Hello Physical Science. Welcome back. We're going to start the last section in Chapter 3 today. The title of this section is Phase Changes. And kind of another way to put this to make it a little more clear is it's going to talk about how we can go from different states of matter. So how we can go from a solid to a liquid and a liquid from a gas and so on and so on. And they call it phase changes, just a little bit of a different terminology here, and it's kind of because we can go between different states of matter in a way you might not usually think. We can go directly from a gas to a solid and directly from a solid to a gas, and that's kind of why they include the term of phase change. So again, to start, as always, talks about our example here. So it says a large iceberg contains enough fresh water to supply millions of people with water for a year. As it moves into warmer areas, the ice changes to liquid water and eventually will disappear. And it says what happens when one substance changes from one phase to another. So that is what we're going to talk about. And there are going to be 6 common phase changes. It says, and then again, just to kind of introduce us here, it says when at least 2 states of the same substance are present, scientists describe each different state as a phase. So a phase change is the reversible physical change that occurs when a substance changes from one state of matter to another. So this is a very important definition. Again, it's a reversible physical change that occurs when a substance changes from one state of matter to another. That is what we call a phase change. And our 6 phase changes are, and maybe you've heard of some of these, a couple of these might be new, are melting, freezing, vaporization, condensation, sublimation, and deposition. So those are our 6 common phase changes. So I'll maybe jot those down now, but I imagine each one of those is going to get their own slide here in a second. To start, so here we have a diagram that lists the 6 physical changes that occur among the solid, liquid, and gaseous phases of each substance. So each arrow in the diagram represents a different phase change. So we will get those all going right there. And as you can see, all phase changes share certain characteristics related to energy and temperature. So this is a really important picture right here. This shows us again how we go from a solid. When a solid melts, it turns into a liquid. When a liquid freezes, it turns into a solid. When a liquid turns into a gas, it's called vaporization. When a gas turns into condensation, it's called liquid. So again, wherever the arrow is pointing, that kind of shows the state of matter, what it's turning into, and the term that we have for it. So this is really important diagram here. So maybe jot some type of version of this down. And again, it's probably not going to be too important because we're going to get a definition of all of those here in a little bit. But being able to read this little picture here saying, well, what is it called when a gas turns into a solid? You should be able to look at this chart and say, oh, that's deposition. When a solid turns into a gas, that's sublimation. So that is, again, important picture right here that kind of really easily illustrates, I think, all of our 6 phase changes and, again, which one they're associated with. So before we get into the specifics of all the phase changes, which we will here in a little while, we're going to talk about what happens to a substance temperature and a system's energy during a phase change. So before we get into the definitions, we have to figure out, again, kind of what's going on, again, in terms of our energy and in terms of temperature. So one way to recognize that we have a phase change is by measuring the temperature of a substance as it is heated or cooled. And the temperature of a substance does not change during a phase change. Now this is really important. The temperature of a substance does not change during a phase change, and we'll go over this here in a second. But whenever water turns to ice, I think they'll give us an example here in a little bit, and the temperature will remain, again, 32 degrees Fahrenheit, 0 degrees Celsius, until all of the water has turned to ice. So while the water is freezing, it stays at that 0 degrees Celsius, and then once all of it has turned to ice, then it will begin to cool even more. So here is, again, a kind of an example of what I just said. So this is a graph of the data collected when a solid piece of naphthalene is slowly heated. The temperature of the naphthalene rises until it reaches 80 degrees Celsius. The temperature remains at 80 degrees Celsius, the melting point, until melting is complete. So again, we're increasing the temperature, we're increasing the temperature, we're increasing the temperature. Again, 80 degrees Celsius is the melting point. So, and if we look, it levels off here at 80 degrees Celsius. So it stays at that temperature until all the melting has completed. So at this 80 degrees, again, so maybe like a quarter of it has been melted, now maybe half of it is melted, now maybe 3/4 have been melted, now 4/5 is melted, now all of it is melted. Now once all of it is from the solid state into the liquid state, that is when the temperature will continue to increase. So you might not think that that's how it works, but again, because when I first learned this, that kind of confused me, but as the phase change is going on, so while it is changing from a solid to a liquid, the temperature remains constant. So that's one way for us to tell that a phase change is occurring. When we see that temperature level off, it is a strong indication, again, that the temperature, or that the substance in question is going through a phase change. And then if the liquid form is cooled, its temperature will drop until it reaches 80 degrees Celsius. It will remain at 80 until all the liquid freezes, and then the temperature at which the substance freezes is its freezing point, and it's identical to the temperature at which it melts. And if the liquid form is heated, its temperature keeps rising until it reaches 218 degrees Celsius, which is its boiling point. Until all boiling is complete, the temperature remains at 218. So again, we can go back to this chart and we can just read it backwards. Again, if we are cooling this substance, so again, it starts off at around 95 degrees. Again, it's in the liquid phase. And when we cool it, when it gets to 80 degrees, it will continue to stay at 80 degrees until it is completely a solid again, and then the temperature will drop. And it is the same for boiling. Okay, so that is how temperature works during the phase change. So now we're going to take a look at how energy works.
Energy!
So during a phase change, energy is transferred between a substance and its surroundings. The direction of the transfer depends on the type of phase change. So energy can either be absorbed or released during a phase change. And actually, if you think back to that elephant toothpaste example we did, that's going to kind of come into play here, because again, if some of you felt that afterwards, it's very hot, and that's going to kind of be going into how we have, again, how energy is released or absorbed during a phase change. So again, as our real life examples here, it says the ice sculpture of a dog sled was carved at a winter fair in Alaska, and the ice sculpture will start to melt if the temperature rises above 0 degrees Celsius or sunlight shines directly on the ice. So again, that is going to mean, again, it is absorbing energy from, again, the sunlight. And this is what we call an endothermic change, where the system absorbs energy from its surroundings, and melting is an example of an endothermic change. So the fact, again, that this sculpture is absorbing the energy from the sun makes it an endothermic change. Again, when you absorb the energy from your surroundings, it's an endothermic change. And then we have, again, a specific term for how much energy that actually can absorb. And again, it talks about 1 gram of ice absorbs about 334 joules of energy as it melts. And this amount of energy is the heat of fusion for water. And the heat of fusion varies from substance to substance. So during an endothermic change, again, it absorbs it. And how much energy it actually absorbs is known as the heat of fusion. And again, that's different from each substance. So kind of on the flip side of that, energy can also be released. So during this example, it says energy released as ice forms on these strawberry plants keeps the plants from freezing at temperatures slightly below 0 degrees Celsius. So again, these strawberry plants are going to be releasing energy. So 1 gram of water releases 334 joules of energy to its surroundings as it freezes, the same amount of energy that is absorbed when 1 gram of ice melts. So as water freezes, it releases heat. The flow of heat slows the drop of temperature and helps protect the crops from damage. And during an exothermic change, the system releases energy to its surroundings, and then freezing is an example of an exothermic change. So again, it's just not necessarily that things are cold, it's the absence of heat. So during an exothermic change, all of the heat is released, and that is what causes it to freeze. Okay, so that's it for this video. Let me know if you have any questions.